Well, it's my pleasure to introduce Flavio Calmon. He's a assistant professor at Harvard School of Engineering and Applied Sciences. Prior to that, he was a postdoc at IBM Research, and he did his PhD in electrical engineering just down the street at MIT. And his work is about applying information theory and understanding robust, reliable, and responsible, trustworthy machine learning. So I think it'd be a lot of interest, and I'm happy to have him here.
Cool. Thanks for the nice introduction. And I'm really excited to be here to talk about some of the work my group has been doing. And today I selected one specific problem that we call multiplicity in machine learning, and I'll be talking more about it. So the work that I'm going to talk today was done by an amazing group of students and postdocs and collaborators, and Sean, who were Carol and Lucas, who were my PhD students. So Lucas and Carol are still my PhD students at Harvard, while I was now a postdoc. Bogdan Klinic, who's just defended his PhD in EPFL and was a visiting student with us. Charlie Marks, who was an undergrad intern with my group and now is a graduate student at Stanford. Carmela Troncoso, who's a faculty at EPFL and advisor of Bogdan. And Berk Ustun, who's a former postdoc at Harvard Circus. And now he's a faculty at UCSD. As probably most of you know, data-driven algorithms are increasingly used to support decision-making and applications of individual level consequence. So these are applications that can have significant consequence in someone's life. The applications such as education, right? This is a picture from the protests in the UK from a few years back, where the British government decided to use an algorithm to grade the A-level exams instead of holding the exams in person. This algorithm, there was widespread evidence that it would be skewed against students that came from lower performing schools, generating these protests. Data-driven algorithms are also used across the world. I'm Brazilian. This is a piece of news from the Brazilian government from last year. This is in Portuguese, but the announcement here is the decision to use an AI algorithm, a machine learning algorithm, to grade the essay component of the university-wide, the countrywide university entrance exam. This is an exam that I took, and the handwritten essays, the plan is to grade it using AI, right? So if you're using, this is an algorithm used in a critical situation that controls access to a critical opportunity in society, access to higher education. And you want to make sure that these algorithms are developed responsibly. And these algorithms are used in cases where they probably shouldn't even be used. For example, this is also a news article from last year criticizing Microsoft's use of AI to predict teenage pregnancy in the province of Salta in Argentina. And similar initiatives are being replicated throughout South America and other places. So we want to develop these algorithms in a responsible way. For example, we want to ensure that they do not discriminate. This sentiment is really nicely encapsulated by the recent blueprint for an AI Bill of Rights by the White House, where they state that you should not face discrimination by algorithms and systems should be used and designed in an equitable way. The challenge of designing trustworthy machine learning algorithms is a difficult one. This is a multifaceted problem. That involves not only technical solutions from practitioners and from ML experts and information theorists and computer scientists and so on, but also collaboration with folks that work with law, ethics, and stakeholders in these problems. And there's also many aspects of making a machine learning algorithm or data-driven algorithm trustworthy. My group at Harvard works or has been working with 4 of these aspects, basically group fairness, trying to answer how can we reduce performance gaps across population groups? Fair use, can we verify if more data in fact leads to a tailored improvement in performance for every individual who provides that data? Predictive multiplicity, when are decisions made by machine learning models arbitrary? And also we've done a lot of work on privacy, trying to answer the question, what information do machine learning models contain about their training data set and what privacy risks does this pose? And we approach these problems using information theory. That's our tool set of choice. And just to give you a sense of how our work happens is that we usually approach problems through these 4 steps, where we start with the problem and usually develop a model that abstracts away computational considerations and focus on the underlying information as modeled by probability distributions and their divergences. And then we analyze these problems using tools from probability theory, statistics, optimization, functional analysis, and so on. And success is achieved if we can translate these theoretical insights into either new operational limits of information systems, trade-offs between privacy and utility, new algorithms, coding techniques, and so on. And so information theory, if you're not familiar with, it's a branch of computer science and electrical engineering that studies fundamental limits of communications and data storage, but also finds applications in many other areas such as probability theory, statistics, mathematics, economics, computer science, and so on. And what my research group does is that we add a new petal to this flower, and we use information theory to understand limits of trustworthy machine learning, focusing specifically on aspects of fairness, privacy, and reliability. And just for the electrical engineers in the room or the folks who work or have worked in the past with information theory, I just want to mention that this is a natural progression of this field. Information theory is a field that actually has a birth date. You can argue that it was born with the publication of a mathematical theory of communications by Shannon in 1938. And the reach for these limits over the next decades led to development of reliable data communication schemes and methods for transmitting, storing, and processing information at scale. Today, all this collected information is being fed into learning algorithms and fueling the fast development of machine learning that is producing new emerging challenges. And what my research group asks is, can we apply tools from information theory to address these challenges in machine learning, specifically challenges in privacy and reliability and challenges in fairness? And today I'm going to focus during this talk in one of these challenges, and it's a problem we've been exploring called predictive multiplicity. Then the rest of the talk will be centered around what predictive multiplicity is. And to do that, I'm going to start introducing this effect. I'm going to explain what the Rashomon effect is and what is predictive multiplicity. This is based on two papers, one from ICML a few years back and a paper at NeurIPS last year. Then I'm going to talk about predictive multiplicity and differential privacy. For folks working on privacy and differential privacy, I hope you find this interesting. This is based on a FACT paper that we had this year. And finally, I'm going to briefly talk about a recent NeurIPS Spotlight paper that we're going to present next month on arbitrariness and group fairness interventions. And if I have time, I'll address a few ongoing research challenges. Okay, are you with me? Good. So we're going to start talking about predictive multiplicity and the Rashomon effect. And I'm going to do that starting with a stylized example, and then I'll give you some examples on real data sets. So to talk about predictive multiplicity, first we have to talk about the Rashomon effect. So the Rashomon effect, assume that you have a data set where each sample is denoted by this random variable X. And we feed these samples to a model, right? We are going to use these samples in this training data set to fit the parameters of a model, for example, the weights of a neural network, or maybe fit a random forest, a boosted tree, something of that nature. And we're going to do that in order to predict a given label Y. For example, if these X-ray images here contain or do not contain, is there evidence of pneumonia, yes or no, in each one of these X-ray images. Well, during training time, the way you would usually do this is via backpropagation and so on. You would fit the models using something like SGD. And during this process, there is a bunch of arbitrary decisions that you will make, right? You're going to, for example, set the random seeds that you're going to use to initialize your model. That will choose a weight initialization strategy, maybe fix the dropout rate that you're going to disconnect in your own neural network, shuffle your batches, and so on. All of these are some random initialization of your network. Now, as you change this random initialization and retrain the model, you may end up with different models in the sense that these models have completely different parameters. But when you evaluate it on a test set, for example, you choose a loss function, say 0, 1 loss, and evaluate the loss achieved by each of these models, their loss might be quite similar. For example, they might be below a given threshold epsilon. Your error rate is below a given value. So this phenomenon where you have multiple models that are different but achieve similar performance in a given learning task is known as the Rashomon effect. This was introduced by Leo Breiman. This term Rashomon effect, as far as I know, was introduced by Leo Breiman in his 2001 paper on the true cultures, where you have many different models having approximately equal accuracy. And the term Rashomon comes from the Akira Kurosawa movie, Rashomon, where different people explain or describe the same crime from different perspectives, giving conflicting explanations. And just intuitively, just to gear up why this happens, in neural networks at least, you can think about having a very non-convex loss landscape that, depending on the arbitrary decision that you make of initializing your SGD, you might end up at a different local minima, and that might give you a completely different model. And critically, the extent to which you observe this Rashomon effect depends on several factors, but one of them is this Rashomon parameter, this level set where you're going to determine which models have conflicting predictions. And you can think about the Rashomon effect almost like partitioning or partitioning your hypothesis space. So for example, the space of all neural networks or the space of random forests into these islands of well-performing models, right? Of models that have comparable loss or comparable accuracy. And this set of competing models is what we call the Rashomon set. It's a level set. It's a set of models whose loss is below a given threshold. Okay. Any questions up to now? So is the Rashomon effect inevitable, right? Are we always going to observe it? And I would argue that yes, there are two factors that drive the Rashomon effect, or maybe others, but certainly two of them is randomness used during training can produce many different models. You can do this experiment yourself. You can train your networks and just initialize them with different initializations, and you're going to end up with completely different weights. And the other, I would argue, more information theoretic factor that contributes to this Rashomon effect is that we simply may not be able to distinguish models using test sets with finite samples. And just to show you this is a collection of 100 random forests trained on the UCI ABLE dataset. So this is your standard ABLE dataset where we predict income from census data. And here we trained 100 random forests simply by using different random initializations. And you can see that on the test set, the bootstrap confidence intervals for your cross entropy loss overlap, right? So if you were to say which model of these are better, you would have a hard time choosing that. Like all of these models have approximately computationally indistinguishable performance. And I'm not going to talk about that today, but we have converse results that show that naturally, if you have a finite test set, there's a limit to the precision to which you can distinguish the performance between two models, simply because you're limited by the number of samples that you have. This hypothesis test will fail, and you can find more details on that in our recent ISIT papers. Okay, so the Rashomon effect, we have multiple models with similar performance, but these models are different. It usually occurs because of different random initializations of your model, and also because of our statistical inability to distinguish the performance between competing models. And the Rashomon effect creates opportunities to improve models without compromising accuracy. So it creates both challenges and opportunities. I'm going to talk about the opportunities first. So theoretically, if we could characterize this Rashomon set, if we could identify this space of good models, I'm not saying we can do that exactly, but just as a thought experiment, if we could do that, we could potentially search in this space for models that satisfy additional criteria in addition to accuracy, to performance. For example, models that might be more interpretable, potentially better calibrated, potentially that satisfy additional fairness criteria, and so on. And there's a recent line of work by Cynthia Rudin, and particularly her graduate student, Lesia Semenova, who's been exploring this, work by Emily Black, who was a graduate student at CMU and now is at Stanford, work by Coston and others, who explore this Rashomon set to either measure generalization of models or, for example, find models that satisfy additional criteria. So this is the Rashomon effect. So the Rashomon effect, just recapping, it happens when we have many different models that have approximately equal accuracy, but these models are different. So predictive multiplicity is closely related to the Rashomon effect. Predictive multiplicity occurs when we feed one sample into these competing models. They might produce conflicting predictions, right? So even though on average, these models are approximately equally accurate, for individual samples, they might conflict, they might disagree. And this phenomenon where we have competing models assigning conflicting scores to individuals is what we call predictive multiplicity. I saw a hand being raised on Zoom. So if you, Matt, if you want to go ahead and unmute yourself and ask a question.
Yeah, so does your argument extend to convex classifiers like support vector machines?
No, that's a great question. So when you have a convex classifier, in the sense that your loss function is convex in the parameters of the classifier, your Rashomon set will be a convex set. And in that case, in theory, if we have infinite samples, we can find a single best model, unless you have some kind of flat minima, but usually that's not the case if you're using cross entropy loss and so on. But if you're evaluating—
you do have
yes,
the same problem of finitudes and also
exactly. And
cubic
in
amount
that
of work to get to the optimum.
Exactly. And in that case, your epsilon cannot be necessarily be made 0 or exactly the minimal loss, because if you have finite samples, you're always going to have statistical uncertainty, some confidence region around your loss if you're evaluating your model on finite samples. But then you would have only a convex set here. You wouldn't have these separated islands. I hope that answers your question.
Yeah, but then going from there, you can always apply a homotopy method to make something approximately convex at the right, with the right annealing schedule. So then by extension, it could apply to SGD as well.
Interesting. I'm not super familiar with those methods, but yeah, would be happy to discuss later.
Okay.
Thanks. Okay, so and predictive multiplicity, as far as we can tell, it occurs in many classification tasks. So this is just one example from our paper from Europe last year, but there's many more examples from a paper by Alex Damur and a team from Google, published at JMLR a few years back, where we just train different convolutional neural networks and image classification, text classification, and audio classification tasks. And you can see that you can easily produce models that have very similar loss, in this case, cross entropy loss. But when you have 5 different models, and when you ask them to classify these different individual samples, they produce conflicting predictions. So who cares, right? So we have these different models and they produce conflicting predictions for individual samples. Why should we be interested in this problem? Well, I think the challenge of predictive multiplicity, where it can become harmful, is when your models are used in applications with individual level consequence. So if predictive multiplicity is not accounted for, decisions supported by machine learning models may depend on arbitrary or unjustified choices made during model development. So think about, again, a model being used to grade an essay for a university entrance exam. You want to make sure that that model, a grade for that essay wouldn't change by plus or minus 10 points if someone just chose a different random initialization for your neural network. And there's a very nice paper by Creel and Hellman where they argue that this is particularly challenging when you have things like algorithmic leviathans. These are algorithms that control access to critical opportunities. Think about like credit scoring, right? Where if we want to have access to credit in the United States, we have 3 algorithms that apply to us, 3 credit bureaus, and they're probably going to get the middle score to determine your credit worthiness. So you will also want to make sure that these algorithms are developed responsibly. And where predictive multiplicity can be particularly harmful is when it's resolved silently, when a single best model is chosen and deployed without accounting for the existence of potentially conflicting models. So this is predictive multiplicity. So the very first thing you want to do if you recognize the challenge is to be able to measure and report it. So how can we measure predictive multiplicity and report this conflict in scores at an individual level? So there are a few strategies to do that. I'm going to mention 3 of them. 2 of them for binary classification, one for when your output is a thresholded decision, a 0 or a 1, and another one that's not my work. This is work by Jamil Watson-Daniels, David Parks, and Burke Ustun for probabilistic binary classification. And reporting score conflicts when you have multi-class classification problems is a little bit more challenging. And I'm going to talk about one metric for that from Europe's last year. It's actually 22, not 23, on Rashomon, called Rashomon Capacity. And just to measure this, I'm going to assume that we have some approximation of the Rashomon set. And the goal is to compute score variation for individual samples across this set. How to approximate the Rashomon set, I'm going to talk about that a little bit later. But for now, I'm going to assume that we're given the set of conflicting models, and we just want to measure score disagreement. So let's start with the most basic case, binary classification. So where each model is outputs a 0 or a 1, right? So binary classification case. In this case, one strategy for measuring predictive multiplicity is that you estimate an empirical Rashomon set. So you try, given a data set or an auditing data set, and given a reference-based model, for example, the empirical risk minimizer that you found by solving a loss minimization problem over your training data, you define your Rashomon set as centered around your empirical risk minimizer, where here L hat denotes the empirical loss, in this case, 0,1 loss over your data set. And given that you can produce models in this set, you can measure predictive multiplicity. So we say that predictive multiplicity occurs if you can find at least one model in the set that produces a conflicting prediction with your base classifier for a sample xi. And you can measure the effect of predictive multiplicity in aggregate across the data set. So for example, for this evaluation data set here, you can measure ambiguity, which gives you the maximum disagreement here, discordance between, for each sample across the data set. So for each sample, you're going to find a competing model that produces disagreement, and you're going to average that across your entire data set. You can measure discrepancy as well, where you try to find a model that across the samples has the maximum amount of disagreement. So the difference here is that the max is either inside, where models are chosen on a sample by sample basis, or an average across the data set, in or out of the summation. So you can have also a similar metric for probabilistic-based models. So in this case, your output is a risk score. It's not a binary decision 0-1. It's a number between 0 and 1. And you can define the empirical Rashomon set centered around the base model in the same way. An interesting metric here, you can define ambiguity and discrepancy the same way we had before. You can also define viable prediction range. So this is a metric on sample by sample basis. This was proposed by Jamil Watson Daniels, where you have the minimum and the maximum score for each sample across this data set. So the lowest score and the highest score for each sample. So this is a very natural metric in binary classification. Now, reporting score disagreement in multi-class classification is a little bit trickier. Because in this case, you have an individual sample that's fed through these models, and what you're going to get is a vector, right? The vector on the simplex, that's going to be the probability of each class. You can think about that as the softmax readout layer of a neural network, right? You're training, I don't know, Cypher 10, and you're going to feed an image, and you're going to get a probability over distribution over 10 classes. And in this case, how do we measure score disagreement? So, we just for introducing a little bit more notation, we can, for each individual sample X and for a Rashomon set determined by a given level epsilon, we can collect hypothetically the set of conflicting predictions, right? These conflicting scores. And our goal is to measure score variation, is to create a function that maps for each individual sample the set of conflicting scores onto a number that will capture the worst case disagreement across classifiers, kind of like the viable prediction range. And we want this function, M for multiplicity, it's a multiplicity metric, to satisfy certain properties. First, we want it to be between 1 and C, where C is the number of classes that you're predicting. For example, in Cypher 10, C would be 10, right? We want multiplicity to be 1 if all predictions in your conflicting models match, right? So for that sample, for example, all of these predictions are exactly the same. And we want it to be C if you can find models in this Rashomon set such that each one of the classes is perfectly predicted. This is the case where you have perfect multiplicity, you can find models that have perfect disagreement. And finally, you want this metric to be monotonic in the sense that if I augment the set of conflicting scores, your multiplicity metric will not decrease, right? So the more competing models that I have, the more multiplicity that I will observe. So how do we build such a metric? So in order to do that, we actually use information theory. And the key idea is that given a set of competing models, you can think about the prediction for a given sample, the conflicting predictions for a given sample as rows of a noisy channel, right? Or for example, rows of a stochastic matrix, right? Of a Markov transition matrix. But again, remember that each score is a number that is a vector that adds up to 1 of probabilities. And you can think about that as rows of a noisy channel and compute the capacity of that channel, just like vanilla Shannon capacity. This is the expression for computing capacity. This is a variational form of capacity. Usually when you see Shannon capacity, it's maximized mutual information over all input distributions of a channel. This is exactly the same thing but written in this variational form, where we find the centroid score in terms of KL divergence for a given distribution over the models, given distribution over these conflicting scores, and then for each sample, we take the maximum over this distribution. Note that here, this will depend on your Rashomon parameter, and this is a distribution over predictions here. And if you use your KL divergence here, your logarithm here in base 2, the multiplicity metric that we choose is true to this channel capacity here. And this metric satisfies all of these desirable properties here. Like, it's not different. This is a kind of a interesting information theory course exercise to show that all these properties are satisfied by this metric. The choice of KL divergence here is arbitrary. You could use some other F divergence as well, but then the value here that you normalize would change. And the interesting thing here is that we can actually compute this pretty efficiently for each sample using algorithms that are well established for computing channel capacity like the Blahoud-Arimoto algorithm. So, and the interesting thing about this metric also is because of its convex nature, if you're doing classification over C classes, direct application of Carr-Theodori's theorem says that there are at most C models that capture the score variation for each individual sample. What that means is that even if your Rashomon set has a continuum of models, right? For example, it has many and infinitely many models. For each sample, there's at most C models that capture the most disagreement in your score. So if you report the score variation across the entire Rashomon set, or just for these C models, you will get the same value of disagreement as measured by Rashomon capacity. Okay, so how does this look in practice, right? How can we actually use this to measure this disagreement across models and actual settings? So I'm going to give you one set of examples where we get a training data set. I'm going to give you results on 4 data sets. One is the HSLS data set. This is a data set where you predict student performance based on questionnaire answers. The COMPASS data set, which is an arguably overused data set in fair machine learning, but the prediction task here is recidivism prediction. There's a UCI adult data set, which is income prediction, and CyFAR-10 for image classification. And what we're going to do is that for the training data, we're going to fit the empirical risk minimizer on a training set. Here, our model will be a very simple feed-forward neural network. And then given test data, we're going to approximate the Rashomon set by something called adversarial weight perturbation. What that means is that we're going to perturb the weights of the network a little bit so that your loss doesn't change by a lot, but in a way to maximize score disagreement, right? So for each sample, we update weights in a direction that maximizes score change, but doesn't violate our restriction on finding a model that has worse empirical loss. And we're going to add these models to the Rashomon set, and then we're going to compute score variation for each point on the test set. So this is the results. So what we have here on the top is for each data set, we report this multiplicity metric. Again, it's between 1 and the number of classes that you're predicting. For the top 1% and top 5% of the points that have the most disagreement, the most multiplicity, I'm showing results for 2 strategies here. One is adversarial weight perturbation. The other one is sampling. What sampling means is that we simply retrain by changing the random seed and getting a new model. And you can see that adversarial weight perturbation is pretty effective at finding disagreeing models. And what I want to mention is that, especially for more complex tasks, just with a very small Rashomon parameter of the order of 2 or 5% or 2% in your loss, you can already find a lot of samples where you have a lot of disagreement across classifiers. And one thing that we consistently observed is that many data sets have a high multiplicity tail. What that means is that if you plot the cumulative distribution of your multiplicity metrics, this multiplicity doesn't impact all samples equally. There's also usually a small fraction of samples that have very, very, very high multiplicity. And that's usually a combination of samples being either close to a decision boundary, even though decision boundaries, when you have soft outputs, like score outputs, that they don't really influence much, and also a point being an outlier. But we are not entirely sure what are the factors that drive this high multiplicity. So you can find many more results in our paper. Any questions up to now?
Yes. So how is this actionable in say, a credit rating department or a hospital that's deciding who to treat?
Yeah. So I think the first step is measuring the phenomena. And the second point is either reporting that for each individual sample. Just like we report test performance, you should probably be trying to measure and report this multiplicity effect, saying like, well, I'm using this model there, but there may have existed another model that would produce a conflicting prediction. And use that almost as a measure of trust or uncertainty in your prediction. The second way of using this is try to create more stable training pipelines. And I'll talk more about that a little bit later. So for example, maybe gearing towards ensemble models, where if you were to repeat the training process, you would observe consistent predictions.
Yeah, I was also going to ask, numerically, do these graphs require training many models?
In this case, no. It does for the sampling strategy here, because sampling requires retraining. The adversarial weight perturbation, no, you just train one model, and then you take gradients in the direction that maximizes score disagreement while preserving performance. But to be clear, these are all like approximations of the Rashomon set. They're far from exact characterizations of these sets.
Would it be like a lower bound on it then?
Yeah.
Because it's search down.
It's a lower bound. Yeah, that's a nice one for you. Okay, so now I want to talk about predictive multiplicity in differential privacy. And this is based on a paper published this year at ACM FAccT'. So in one place one application where we actually add noise during training is when we want to ensure some measure of privacy on our training data, and specifically differential privacy. And if you're not familiar with differential privacy, I'm going to give you like a 3-slide crash course on what differential privacy is. So again, this is our training pipeline where we have a set of samples and we have our model. And for example, we're all putting a label 0 or 1, positive or negative, pneumonia in this image. And now we're going to assume that our training data is privacy sensitive. In this case, you can think about the training process, or in general, you can think about the training process as a randomized mapping from data to model weights, right? If you're solving a convex optimization problem, this is not randomized, or at least it's randomized in the sense that all the mass concentrates in one output, your minima of your optimization problem. But if you have some kind of randomized learning algorithm, you can think about this as a randomized mapping. And in this case, your weights, the output of your training process, will be a random variable itself, depending on your learning algorithm. So, and just as a sneak preview, in differential privacy, we add noise. So each time you retrain, you get a different set of weights. You can think about this as generating another realization of this random variable. So differential privacy, the goal of differential privacy in machine learning is to ensure that small changes in the training data set does not significantly change model parameters post-training. So for example, if we were to change this first sample, just change one sample, or using this notation, if we were to produce another training data that's neighboring to my original training data, so this still the relationship is neighboring in some sense, for example, changing one sample, we say that your training algorithm satisfies epsilon delta differential privacy if for any output event here, or any value, for example, that this output can produce, the probability of observing a set of weights or parameters within this set E is at most within a multiplicative factor of e to the epsilon and an additive factor of delta for a neighboring data set, where the supremum is taking over all neighboring data sets. So intuitively, you can think about these epsilon and delta parameters as measures of privacy. The smaller they are, the more privacy you have. And it tries to ensure that your training process, you don't observe, the probability of observing a given set of weights doesn't change much if we change the input training data by just a little bit. How is differential privacy usually ensured in practice in machine learning? And in practice, it's usually ensured via some measure of randomization. So for example, there are many strategies for ensuring differential privacy. One of them is output perturbation. So for example, we train our model, and we get the weights, and then we add noise to the weights in order to mask potential differential changes in the input of the training data. There are strategies such as objective perturbation, where we add a random linear penalty to the objective function that we're minimizing, and the goal of that is also to mask small changes in our data. The most common, I would argue, today in training large models is DPSGD, right, where we add noise to gradient updates in order to mask small changes in the training data. But in general, you can think about this as randomness that we add during training in order to ensure privacy. Now, the challenge here is that each time then we run our training algorithm, a different model is produced. So simply by changing the random seed that changes, that determines the noise that we're going to add during training, we might end up with models that have pretty different weights, right? And these models individually, they offer the same level of privacy, and they can offer even approximately similar accuracy, but they might produce conflicting predictions on individual samples. So the cost of privacy, here of privacy is a degree of arbitrariness in the weights of your model, and consequently, a degree of arbitrariness in predictions. And the important point here is that this arbitrariness cost of differential privacy does not affect all samples equally. So by adding privacy, certain samples will receive more arbitrary outputs than others, in the sense that if we were to retrain the model, we would observe a different prediction for that sample. And just to give you one simple example of that on synthetic data, this is an artificial example that I'm going to show on two-dimensional mixture of Gaussians. Your most basic classification task, you have two-dimensional Gaussians. We're going to have an objective perturbation mechanisms and fit a logistic regression classifier. And we're going to train 5,000 models on the same data, keeping models that are within 80% accuracy of a baseline. This is not a differential private training strategy. So obviously, like, we're violating privacy here if you were to disclose these 5,000 models or even control for accuracy, but just for the sake of seeing what is the impact of this randomization in our training process. And what I'm going to report is 2 times the probability that a prediction changes after retraining. So 1 means that your prediction is basically a coin flip, right? In the sense that if I were to retrain the model, I would get a different prediction. 0 means that your prediction is consistent. And here's the example on a mixture of Gaussians. So without privacy, my optimal classifier is this 45-degree line. It's this linear separating region here. And as you can see, the points in the dark region here, like the lower the value of epsilon, the higher the privacy I have. So the more privacy I have. And you can see that as I change privacy, the probability of like predictions for particularly in these 2 cones here at the edges become pretty random. Meaning that a point here, for example, this point, if I were to look at the prediction for this point here, or this point here, even though it's not that close to the boundary, just by adding privacy, the probability that that prediction would change if I were to retrain is pretty high. And the challenge of that is because, for example, if your data is this point here, you might be thinking that the predictions made by the model is due to features that you added, but in fact, it's simply an arbitrary artifact of noise that I added during training in order to ensure privacy. And we have in our paper many more examples on different data sets on how this disagreement behaves with different privacy parameters. And what we observe is that this disagreement is prevalent across different data sets. It doesn't impact all samples accurately. So the cost of the arbitrary cost of privacy, this arbitrariness cost, is not equally divided across all samples. And often it's not equally divided across groups as well. It might impact some groups more than others. And an open problem, and this is, if anyone wants to work on this, I would love to chat more, like something that we do not know how to build yet, is how do we actually report predictive multiplicity and differential privacy? How can I give a user of a model an assurance that the prediction that you observe from this differentially private training model is consistent in the sense that it wouldn't change if I were to retrain the model just by changing the seed of the noise, the noise generator during training. And how can I ensure this, give the user this certificate that this is a prediction, that this prediction is consistent, it's not an artifact of noise, in a way that is also differentially private, that doesn't violate differential privacy of your training data. So that's a predictive multiplicity and differential privacy. And now I'm going to talk about arbitrariness and group fairness interventions. And this is a NeurIPS spotlight paper that we're going to present in a few weeks in New Orleans. So what I'm going to talk now about is this relationship between individual fairness and group fairness, which is a common desideratum in trustworthy machine learning. So could you talk first a little bit about group fairness in case you're not familiar with it? So here again is our setup where we have a data set and we have a sample X that we feed it to a classifier like a neural network, and we have our predicted output H of X. And very frequently in practice, we observe that these classifiers can have a difference in performance and average performance across different population groups. This challenge is the challenge of addressing this challenge is addressing the challenge of group fairness, where classifier performance should not significantly change across groups in your population. Usually these population groups are predefined, things like age, sex, race, ethnicity, presence of a disability, and so on. And performance is usually measured in terms of difference in accuracy, false positive rate, false negative rates across different groups. So exactly what metric you should choose really depends on the application at hand. And there are many, many interventions out there that aim to reduce these performance gaps across machine learning models. Roughly speaking, this is not an exhaustive list, but roughly speaking, these interventions can be categorized in terms of pre-processing methods, where in order to reduce this performance gap, you change your training data in some way. In processing methods, where you add a penalty or something of that nature during the training process in order to ensure group fairness, and post-processing, where you try to post-process the output of a classifier in order to ensure fairness. And the way these methods are compared are through benchmarks that look like this. This is a paper already a few years old now by Sorel Friedler and their team at Haverford College, where they compare several fairness interventions across different data sets. And the reason I'm showing you this is just to show how these models are compared. These interventions are benchmarked in terms of these fairness accuracy plots, where you have a data set, for example, Compass data set. On the x-axis, you have some measure of group fairness, difference in false positive rates or difference in average outputs. On the x-axis, you have the accuracy of your model, and you try to be in this upper left corner here. You try to get maximum accuracy and the smallest group fairness violation. And each dot here represents the performance of some group fairness intervention on one model on that given data set. But usually these models are compared in terms of these fairness accuracy curves. And as I mentioned, there are many group fairness out there. Like there was a recent survey that identified 241 publications and over 400 methods that try to optimize this fairness accuracy trade-off. So the question that we ask is, do group fairness interventions also control for predictive multiplicity? Or are these orthogonal facets of trustworthy machine learning? So in the sense that if I train my model and I apply a group fairness intervention, does this decrease arbitrariness and lead to more consistent predictions, or does it not decrease arbitrariness? Could it even increase arbitrariness? And just as a warm-up of this interplay between group fairness and predictive multiplicity, and as a spoiler, yes, it can increase arbitrariness. Let's look at the simplest classification task that we can think of, a one-dimensional classification task. And in this case, I have two attributes, S, which is a sensitive attribute that just for simplicity, just for the sake of example, we're going to assume it's binary, 0 or 1. This denotes membership in a group, and we're trying to predict a binary outcome Y. We're trying to predict that. What we observe is some feature X. Again, this is just a synthetic, simple example of one-dimensional value X. It's a real number, this random variable, and for each value of S and Y, X will have a given distribution. So, for example, here, when Y is 0 and your group is 0, it's going to be a Gaussian centered in -1. And when S is 0, but Y is 1, this is the distribution for group 0. And you can have the similar distributions for group 1. This is a synthetic example that we have. So the classifier that we're trying to fit is a simple thresholded classifier. So we're just going to pick a threshold T, and I'll put 1 if X is greater than T or 0 otherwise, right? And set this optimal threshold in order to maximize accuracy, minimize error. And in the simplest case where we assume that S and Y are uniformly distributed, the question that we ask is, what is the probability that Y is different than H of X for different thresholds T? Then it's easy, you can just plot this, right? And just see the value of your probability of error for different T's. And in this case, your most accurate threshold is T equals 0, just by design. Like that's the threshold that gives you the highest accuracy. So let's look at a group fairness metric at this threshold, right? So again, we have two groups, and the group fairness metric that we're going to look at is something called equal opportunity. This is a fairly widely used metric where we're looking at the difference between the average difference between true positive rates and false positive rates between these two groups. If this value is 0, it means that your error rates are the same. And we can plot this metric here, and we can see that this is your mean EO violation. So at your optimal point here, you actually have quite a bit of mean EO violation. So let's say we want to reduce this violation to 10.1, a 10% difference on average across both groups. So now you have two solutions that maximize accuracy for your given fairness constraint. So basically, you can either operate in this solution or this solution, and both of them will give you the same value of accuracy and group fairness, right? But these are very different classifiers. Specifically, if you're a point whose feature is within the shaded region, there are two equally fair and accurate classifiers that would produce conflicting predictions. So by adding the fairness constraint, right, I actually increased the number of classifiers that are fair and accurate, adding multiplicity to a problem that didn't exist before. And this is due to the highly non-convex nature of these fairness constraints here. It's non-convex, you can see the shape of the curve because it's based on differences in error rates. And I'm running out of time here, but like you can do the same exercise, for example, two-dimensional classification and so on. So at first, this might seem not very intuitive because by adding a constraint to a problem, you would assume that we're actually reducing the number of feasible solutions, right? But in this case, that's not necessarily the case because by adding this constraint, we actually multiply the number of good solutions that satisfy a given fairness and accuracy constraint. So let's see how this works in practice. So what I'm showing here are standard like accuracy fairness curves. Here we get a data set. In this case, this is the ENEM 50K data set. This is a data set based on the Brazilian University entrance exam, which this is an open data set with millions of samples, and we get a subset of 50,000 samples just to benchmark these different samples. And we train a random forest classifier and evaluate in terms of accuracy and fairness metric. So if we train the random forest classifier without any fairness intervention, we get a really high accuracy, but quite a bit of disparity of performance. So this is the start point here. And each one of these different lines is a different fairness intervention, right? That aims to maintain accuracy while closing this performance gap. So for the purpose of evaluating multiplicity, what we're going to do is that we're going to change the random seed that we use to initialize our random forest and just rerun the entire pipeline of training the baseline classifier and applying the fairness intervention just by changing the random seeds. We're going to do that 10 times. And of course, now instead of having a single curve, we have a point cloud, right? One for each retraining. And you can see that these accuracy fairness metrics are pretty much still the same. They're pretty stable. So if we zoom into one of these methods, I'm going to look at the reductions approach. The reductions approach is by Agarwal et al., folks from Microsoft, and this is one of the state-of-the-art methods, if not the state-of-the-art method for ensuring group fairness in binary classification tasks. And I'm going to evaluate these different solutions. So the solutions here, here, and here, right? So these are solutions that have approximately the same fairness values and approximately the same accuracy, and evaluate them for predictive multiplicity. And what you can see is that if you look at the standard deviation of scores for each sample, so across these 10 models, we compute the standard deviation of the output and plot the quantile of the score standard deviation, this cumulative distribution over the standard deviation, we can see that compared to the baseline, the predictive multiplicity for a significant chunk of samples, the score standard deviation, this disagreement increases. So what that means is that not all paths lead to the same value of accuracy and fairness. Like these are very different classifiers. And hidden within these standard fairness accuracy plots, you might actually be increasing the arbitrariness of individual predictions for individual samples. So for the specific case of the reductions approach, why does this happen? And one of the reasons that this happens is the thresholding behavior of this specific intervention, that as the way the reductions approach works is that you retrain the model several times and create an ensemble of classifiers. And what we observe is that post-intervention, your scores become more and more threshold-like, even though we're not explicitly thresholding. And this leads to this higher score variation. And even if you threshold the baseline and compare with the post-intervention score standard deviation, you can see that there's a significant increase in standard deviation. So like before the random forest has a given multiplicity, right? If you retrain a random forest, you might observe a multiplicity, and that multiplicity is increased post applying your fairness intervention. So how do we handle that? Well, one strategy is classifier ensembling. Like you can actually prove that it reduces multiplicity, right? Just by averaging things out, you get a more stable pipeline. So for example, if instead of training one model, we train 30 random forests and create an ensemble of trees, right? So random forest is already an ensemble, and we just ensemble everything together. We can maintain accuracy while also maintaining your fairness, your fairness guarantee post interventions, and basically at about 30 models, we recover the same multiplicity as observed from the baseline. This is not a great solution because now it requires maintaining 30 models instead of one, right? But this is one strategy that we have. Okay, so just to quickly wrap up, I'm going to talk about some ongoing research challenges and some takeaways. So my takeaway is that always measure and report predictive multiplicity, even if we don't know exactly what is the best method to resolve this issue. I think particularly in applications with individual level consequence, this predictive multiplicity should be measured just like we measure test error. Multiplicity is a hidden cost of differential privacy in addition to a decrease in accuracy. And it's hidden in the sense that it's usually not reported, right? A user of a differentially private trained model may not be aware that their prediction will change simply by rerunning the training algorithm. And it may be a hidden cost of fairness interventions. So hidden within these standard fairness accuracy plots, there's a much more complex facet of arbitrariness and trustworthy machine learning. Decisions supported by machine learning models without regard for multiplicity may be arbitrary, and an important open problem is designing efficient methods for characterizing the Rashomon set and reporting multiplicity. How can we do that without training a model, having to train a model 100 times, or having to add constraints to problems, for example, in training neural networks and so on. Yeah. So a few other projects that my group has been working on that y'all might find interesting. We've done a lot of work at the intersection of machine learning and information theory. For example, if you want to know what is the connection between Schrödinger operators, differential privacy, and KL divergence, ask me after the talk. One thing we've been thinking a lot about is simply how do we design noise distributions to add to differentially private training in order to maximize accuracy or maximize utility while ensuring privacy. We've also have some recent work on information threat generalization bounds and on the fair use of group attributes. One problem that I'm interested in and looking for collaborators is the problem of data set compression. These data sets that we use in machine learning have a ton of redundancy. How do we compress it? That actually might reveal something about the information contained on these data sets. This is one example of MNIST just ordered by similarity of digits. And yeah, I'll be happy to answer any questions that you may have. Thanks.
So I have a question maybe about, in the first part of the talk, you mentioned the adversarial perturbation for kind of finding the different ensembles. Do you think, I mean, with that, and then in the last part, you talked about ensembling as a technique for doing it. Do you think adversarial perturbation could be useful for finding ensembles in the last part?
I think it could, especially for neural networks. I think adversarial perturbations could be a way of generating almost like a self-ensemble where I just perturb the weights and look at the change in the outputs and try to smooth that out in order to ensure multiplicity. There's a recent paper that was posted on Open Review for iClear that tries to do that by looking at different dropouts. Instead of doing adversarial weight perturbation, you just randomly disconnect some neurons and look at the change in scores based on that. I haven't dug deep into that yet though, but there might be, I'm sure there are better strategies out there instead of just creating vanilla ensembles. Any other questions? Yeah.
Is a group unfairness problem mainly due to the imbalance of the training data in each group?
That could be one source of unfairness. It could come from like lack of representation in the training data set that you're using, but there could be other sources for that. Like it could be just a mismatch for the model class that you used or some weird local minima that you converge to. The data set bias is a source of group unfairness for sure, but it's not the only source.
Is there any work like for the minority group use like generative models to increase more synthetic samples for that?
I think there is. There are work on data set augmentation via synthetic data generation. If you ping me later, I can send you specific references. Yeah.
Yes, good question online too from Matt.
Yeah.
Oh, yeah. So I like the identification of predictive multiplicity with model confidence, but I'm a little less clear on fairness. If I personally am a data point that's near a decision boundary and that boundary is locally not well supported by the training data, I actually might prefer that the treatment that's selected for me is a coin flip, a weighted coin flip. You know, that in some sense is fair than, for example, let's say the model just has a strong structural bias. So I might have low predictive multiplicity, even though I'm not strongly, my treatment isn't strongly supported by any training data, just because you train up many models and they all are fairly consistent because of the bias.
Yeah, that's an interesting point. My view is that that could also be application dependent. If you were to call like having high multiplicity being unfair. I think one important point that I want to reinforce is that I think one of the danger lies when you do not report this phenomena, and also the fact that it's not equally, it doesn't incide equally across every single point. So yeah.
And I wonder if there's some way to tease apart the multiplicity that's due to sparse regions of training data versus the particular architecture of the model of the hypothesis class.
That's a really interesting question. Yeah.
Like if you could have a model specific, I mean, it's kind of a little like doing Bayes risk where you marginalize overall possible parameterizations of the model or measure the variance of the evidence in all Bayesian frameworks so that you're kind of independent of your accidents of training and just are getting a characterization of your entire hypothesis class.
I guess maybe another way of framing it is talking about aleatoric versus epistemic multiplicity, and that which can be resolved with more data or by choosing a better
hypothesis class.
Yeah. Interesting.
Anyway, cool stuff.
Thanks. And yeah, you had a question.
Yeah, so building off the finding on how group fairness actually increased the predictive complexity of the model, would you make a similar conclusion about recent works that make neural networks or the models more immune to adverse attacks? Do you think that would also increase predictive complexity?
Yeah, that's a connection that I think it's worth exploring, because you can think about multiplicity almost like, so in adversarial attacks and robust machine learning, usually you keep the model fixed and you perturb the input. And here to measure multiplicity, we keep the input fixed and perturb the model. So in the sense, they're like complementary approaches. So, yeah, but I guess your point is if we make the model more robust or immune against adversarial perturbations, do we guarantee less multiplicity? I'm not sure. I think that's worth exploring.
Another question is, the number of model you need to train the system depends on the dimension of the model.
No, it depends. Well, it depends on what you're looking at. So here, so let me go back to the differential privacy part. So here, for example, the number of models you have to train in order to create estimates here, we have bounds in the paper, and it doesn't really depend on the complexity of the model. If you view the training process as almost like IID training process, in the sense that you keep your training data fixed and you have this box, and each time I pull the lever, a new model comes out, right? So each time I pull the lever, a new set of weights comes out. And in that sense, like the number of models that you need to estimate multiplicity and disagreement depends on the number of samples you're estimating that in. And actually the trade-off is quite favorable. So I believe the number of models that you need increases with the logarithm of the number of samples. And that comes from the union bound of a Chernoff, like you applying the union bound for Chernoff bound. You can see our paper.